Hello, calculus classes. I hope you're enjoying your 2 snow days off. What we're going to do in this video is 7.1 and 7.2. If you would like the notes, the template of the notes, they will be in the Unit 7 folder, so you can pause the video and print them out if you want them. But this actually will probably help with the Unit 6 test on Tuesday or Wednesday, because we're pretty much doing what we learned in Unit 6 with just one extra step. So we're going to start with 7.2, and we're going to do U substitution with definite integrals. And like I said, you don't have to do U substitution, but occasionally on an AP exam they're going to put a question like this, especially with definite integrals. So I want to make sure we review it so that if there is a question, you are able to do it. So for these, we want to integrate from 0 to 1. It's a definite integral because of the bounds, and we're going to use U substitution. So like before, we're going to let U equal the inside. So I'm going to let U equal 1 minus r squared, and then I'm going to take my derivative of U with respect to r, because that's my variable, and I'm going to take the derivative of 1 minus r squared, which is 2r. And then we're going to solve for dr again. So dr, if I cross multiply, is going to equal du over negative 2r. And then I'm going to replace everything in this equation so that it's all in terms of u. So I'm going to get the square root of u, and then I still have the r, and then I'm going to substitute the du in, or the dr. So I'm going to replace that with du over negative 2r, and if you do your u substitution correct, the r should all cancel. So I get the square root of u, and I'm going to put the negative 1/2 outside because it's a constant, du. Now the step that I haven't shown you yet, which is what's new about 7.2, is that when we have bounds, we can change those bounds in terms of u so that we don't have to change our equation back into r. So what we're going to do is we're going to plug these bounds into my original u equation to get the u bounds. So I'm going to do u of 0, which is equal to 1 minus 0 squared, which is 1. And then I'm going to do u of 1, which is 1 minus 1 squared, which is 0. And so my bounds, the 0 one, I'm going to put 1 for the lower bound now. And then the upper bound now is 0. Okay? So you technically shouldn't put these bounds when you have it in terms of u, because they don't match up. And so now I'm going to do the same process. I'm going to integrate, so this is u to the 1/2. So when I add 1, I get to the 3/2. And if I divide by 3/2, I multiply by 2/3. And then I'm going to evaluate now from 1 to 0 instead. And so then we get, if I simplify this first, I get negative 1/3 u to the 3/2. And then I'm going to plug in 0 and 1. So I'm going to plug in my upper bound of 0. And then I'm going to subtract a negative 1/3. And then I'm going to plug in my lower bound of 1. And then 0 to the 3/2. I wrote that wrong. Let's just fix that. It should be 0 raised to the 3/2. There we go. So 0 to 3/2 is 0, so I get 0, and then 1 to the 3/2 is 1, and I get minus a negative, so that's plus 1/3, and then my answer gives me 1/3. So it's exactly the same what we did, and I said this is actually good practice because we're just practicing with integrals for the test. So same thing here, we have 5r divided by 4 plus r squared squared dr. And then remember, whenever we have something in the denominator, we move it to the numerator, so I get 4 plus r squared to the negative second dr. And so then we want to let u be my inside. So because we have a negative second exponent, the 4 plus r squared is my inside. And then if I take the derivative, I get 2r, and then if I solve for dr, I get du over 2r. Remember, we're just cross multiplying and solving for dr. And now I'm going to replace everything. So I'm going to keep my 5r here for now. The r should cancel eventually. I'm going to replace 4 plus r squared with u, so I get u to the negative second, and I'm going to place dr with du over 2r. And then if I simplify, I'm going to pull out the constant, and then I'm going to get u to the negative second du, because the r's reduced to 1. And then I have to fix my bounds. So I'm going to plug in negative 1 and 1 into my u equation to get my new bounds. So the u of negative 1 gives me 4 plus negative 1 squared, which is going to give me 5. And the u of 1 is going to give me 4 plus 1 squared, which is also going to give me 5. And for this one, it actually makes it pretty easy because I don't even have to evaluate this integral, because I know by properties that when the bounds are the same, the integral is automatically 0. So this answer is going to be 5 halves times 0, which is just 0. So the answer for this integral is 0 when we actually change the bounds. We can see that. And if we did this originally and plugged in my u again and plugged in 1 and negative 1, you would also get 0. And then for the last one, we have cosine of x divided by the square root of 4 plus 3 sine of x. So I'm going to rewrite my function so that I bring the denominator to the numerator. So it's going to be 4 plus 3 sine of x to the negative 1/2. I'm going to let u be my inside, and now we can see that because we have an exponent of a negative 1/2, 4 plus 3 sine of x is my inside. Take the derivative, and we get 3 cosine x, and then I'm going to solve for dx, which is du divided by 3 cosine x. And then if we just do our bounds right now, u of negative pi is going to give me 4 plus 3 sine of negative pi, and sine of negative pi is 0, so we get 4, and u of pi is 4 plus 3 sine of pi, so u of pi is also 4. So we're actually going to have the same thing that we had last time, but just to plug everything in so we check, we would get cosine x, and then we would have u to the negative 1/2, and then du over 3 cosine x from 4 to 4. And if we simplify, we would get 1/3 the integral from 4 to 4 of u to the negative 1/2 du. Okay? And you don't have to, again, it's 0, but just to practice, just in case, because a lot of them on the homework will not be 0. So we would integrate, we'd have 1/3 times u to the 1/2 divided by 1/2, and we're going to evaluate from 4 to 4, and then we would, if we multiply with reciprocal, we get 2/3 u to the 1/2 evaluated from 4 to 4, and then just to practice with plugging in, we get 2/3, and then we have the square root of 4 minus 2/3 the square root of 4, which again is why it's equal to 0. So you didn't, for this one, if the bounds are the same, you can stop here and just say it equals 0 because of the properties, but I just wanted to practice because on the test and on a lot of the ones that practice with this, it won't be the same bounds. The second thing we're going to do is from 7.1. It's on differential equations. So we've done stuff with differential equations. Differential equations are an equation involving a derivative. Okay? And the differential equation relates an unknown function and its derivative. So they usually write it like down here, dy dx is equal to f of x. Okay, and then the antiderivative of this function as an infinite number of solutions. And this is called a general solution. So when we solve these, what we're going to do is we're going to get all the x's to one side and all the y's to the other, so that when we integrate both sides, we're going to get y is equal to, and we'll say capital F is the antiderivative of f, so f prime is equal to f. So if I integrate that, I get capital F of x plus c. So we get the general solution for it. Okay, so when we do this, what's going to happen is if we're given an initial equation and then we can find a particular solution, just like before. So a differential equation with initial condition is called an initial value problem. So we've actually done this already. So like I did before, is when you have a differential equation, what you do is you separate your variables. So when you do this, you're going to get all your y's on one side and all your x's on the other. So I'm going to put dy is equal to 4x to the 7th dx. So I separate my variables. And then I'm going to take the integral of both sides. So the integral of dy is just y, because there's a 1 in front of it. And the y's derivative is 1. And the integral of 4x to the 7th is 4x to the 8th over 8 plus c. And if we simplify that, we get 1/2 x to the 8th plus c. So this is called my general, just like we called it before, general solution. Now they gave me an initial condition or a point, and so I can find c. And so again, this is good practice for the test because this is on the test. So if I plug in 0 for 8, I'm going to get c is equal to 4, and then to get my particular solution, I just plug it back in, and I get 1/2 x to the 8th plus 4, and this is my particular. So it's pretty much what we did before. The only thing is they write the original equation differently. So again, solve the initial value problem dy dt with sine of pi t, where y of 2 is equal to 2. So the first thing I'm going to do when they say solve is I want to find the original equation. So I'm going to separate my variables. Then I'm going to integrate both sides to get the general. So remember there's a 1 here. The integral of 1 is y. Sine of pi t, the integral of sine is negative cosine of pi t, and then I have to divide by the derivative of the inside, which is pi, plus c. So general equation. I'm going to plug in 2 for y, and then plug in 2 for t to find c. Cosine of 2 pi is 1, so I get 2 is equal to negative 1 over pi plus c. So c is equal to 2 plus 1 over pi. And I'm just going to leave it like that. You can make it a decimal if you want. And then the last step is to plug in my c value to get the particular equation. So I get pi t over pi plus 2 plus 1 over pi. So here are the steps that we've been doing. They're called separable differential equations, where they give me dy dx and then we have two functions. So we separate the x and the y's, we integrate both sides, and we only need 1 plus c for all the constants, because a constant plus a constant is just another constant. So you don't have to worry, like if we go back for a second, you don't have to worry about putting a plus c with the y, because you'll just get another constant. Solve for y. If given an initial value, find the value for c, and then write the equation with the value. So that gives me the particular solution. So for this one, solve the differential equation. So I'm going to cross multiply, and I get y squared dy is equal to x dx. So that's the first step. Then I'm going to integrate both sides to get the original equation. So I get y cubed over 3 is equal to x squared over 2. And then I'm going to put the plus c with the x. It really doesn't matter which side, but it's generally we put it on the side with the x. And then we usually solve for y. What I'm going to do first is because it says find the particular equation, I'm going to plug this into here and find C because it will be easier at this point. It depends on the equation when it's easier to plug in C. So here I'm going to plug in 2 for y and 0 for x. And so C is just 8/3. And I knew it was easier because I knew the x term was going to go to 0. And then I'm going to plug it back in, so I get y cubed over 3 is equal to x squared over 2 plus 8/3. And then we're going to solve our equation for y. So I'm going to multiply everything by 3. So I get 3x squared over 2 plus 8 because I have to multiply both terms by 3. And then the last thing is I'm going to take the cube root. And because it's a cube root and odd power, we don't need plus or minus. And then that is my answer. Okay. So if you wanted to keep C in your equation, you could have C here and then you'd plug in your values to find the new C there. But if you plug in C in the original versus after you solve, your C value will be different, but it will give you the same end equation. Okay, so here's the 3 last problems for solving differential equations. So the first one, we have dy dx is equal y x squared, so I'm going to separate again. So I get dy over y is equal to x squared dx. So I divided by y and multiplied by the dx. Then I'm going to integrate. So 1 over y, or dy over y, is the same as y to the negative first. That gives me ln. And I'm going to put the absolute values. And then I get x cubed over 3 plus c. Okay. And this, because it just says solve, we want the general solution, but we always solve for y. So because this is a logarithmic function, we're going to change it to an exponential. So this is like log base e. And so we're going to get we're going to get y equals e to the x cubed over 3 plus c in the exponent. And just so you know, we'll get to this more, but a lot of times what we'll do is we'll separate it so we get e to the x cubed over 3 times e to the c if we use log properties that you can bring it to both. And then e to the c is just another constant, so we usually call it c1. We're going to do a lot more with that, so you don't have to worry too much about it now. Okay, so what I want you to do is pause the video for a second and try the last 2 on your own, and then I'll put the answers up for you to check. So just pause it now and try them, and then you can check the video once you tried them on your own. Okay, so here are the 2 problems solved. So you separate the equations. Tangent of y is the same as cotangent. I solved it up here. So we know that cotangent is cosine over sine, which is sine to the negative first. The integral, so sine is the inside, cosine's the derivative. The integral of something to the negative first is ln, and then if I divide by the derivative of sine, which is cosine, the cosines cancel. So I get ln of sine y is equal to negative cosine x plus c. Make sure you have the absolute value symbols. And then I change a base. So I do e to the other side is equal to just the number. So the ben. And then I can solve for y. So how we solve for y is I'm going to break up the e. I'm going to make it e to the cosine to x times e to the c. E to the c is just another constant, so down here I called it c1. And then to get y by itself, to get rid of a sign, you do the inverse sign. And so this is my equation. So a lot of times they're not very nice equations when you solve. And the last one, so I divided by cosine squared, multiplied by dx. Cosine squared is the same as secant squared. And I know the integral of secant squared is tangent. The integral of e to the x is itself. I put the plus c. It's not in the exponent this time though. And then to get y by itself, I do the inverse. So most of this is practice. It's mostly what we've done. It's just one extra step of separating the variables. And then this will pretty much be your homework the day after the test, but if you have extra time and you want to do it this weekend because of the snow days, it will be page 343, 53 through 65 odd, 71, 73, and then page 331, 1 through 19 odd. And this is probably good practice for the test as well. So if you finished all the review and want extra practice, I'd recommend doing this. And then on Tuesday, there'll be another video. So your homework after the test will be to do these problems and watch the other video. So I hope you enjoy your weekend.